Hello, welcome to chapter 5. Um, Basically, this chapter is energy. We're going to talk all about energy. Before I get into chapter 5, though, I do want to talk about the exam that happened on Friday a little bit. Yeah, exam. So, I always show the average and the max score. The max score was 100. Two people in the class actually got 100%. The average on the exam was a 61.8. This is not including zeros. There's a few people who didn't show up. There's actually someone who has a zero point 0.0 in the course, so I assume they're dropping, and I took them out of all my calculations. A few comments I have on it in general. I'm not going to go through like the solutions of the exam. They're posted on Vanco Hall. I also marked how I graded it on each of your things, so you can go and look, see why you got points off if you did. Um, If you have more questions about your grade in particular, come to my office hours. I'll go through it. I will say, show your work. Like I've said this before, writing your equations to give points. A lot of people didn't write equations; they just put numbers. I'm not going to give partial credits for numbers. I want to see you know the process to do it. I don't care if you have the right answer. I want to prove you get the process. So make sure you show your work. I did give a lot of partial credit. Also, some people complained about time. Though when I show the average on the breakdown, it's less justified. Um, Keep in mind that if it is, you have access to everything, doesn't mean you need to use everything. I can look at the logs of people on Vanco Hall, and I saw a lot of people during exam like opening up notes and loading notes, which is fine, but that just takes time. Be prepared ahead of time. Um, this is the breakdown of grades on this exam. Once again, this is not including the zeros. So, I mean, 9 people got in the 90s, but also 10 people got beneath a 40. It's kind of spread out a bit. With that into play, that makes this the grades in the class, where the average in the class is at 69.5. This is a little lower than I'm comfortable with normally being. But there was something of note in this, and that is there's two students who have less than a 30, right? In fact, if I switch this to letter grades, this is the breakdown, which was really alarming at first, that 38% of the people are failing the class. But I went and looked. Almost all of those people who are failing the class also have a failing grade in lab and homework. There's one or two who only has a failing grade in one of the two. It's not that this exam brought a loud portion of Fs, it was before that. You have to do the work to pass the class. Even if you don't do well on the exams, you have to do the labs and the homework. And the fact that the average in homeworks is like a 60% is really alarming to me. Um, Now, most of you who are failing can get this grade back up as long as you just do the work moving forward. Um, but yeah, it's a really weird grade breakdown. I don't really know what to say about it with way so many Fs and then so many As. So on either side. But as I said, a lot of these Fs are just people who have not been handing in labs and homework. Any questions about the class in general or the exam before I get into chapter 5? Okay. Just so you know, if before people ask, I do not do extra credit and I have no plans to curve. The fact that there's so many grades high makes me think the class is doable. And once again, if it was just the exam was why grades were bad, I'd be looking at this differently. But it's mostly labs and homework that are bringing people's grades down. Um, Please make sure you do your labs and homework. That being said, homework this week, there isn't one. Normally, homework's due every Wednesday at 11, since some people still don't seem to realize that. Um, there was no homework on Wednesday the 10th because the next chapter's homework is chapter 5, which I'm going to start in 2 minutes. So that it'll be due next week. There is still a lab this week. Lab is due, like always, on Thursday the 11th at 3 p.m. This lab excuse me, this lab is going to be on friction. So it's still on the old stuff. The lab on conservation of energy will open this Thursday and be due next Thursday. Once again, check for questions. Anything else, or am I good to get into it?
think we're good.
Okay.
Wait, so the lab it's going to be based off of chapter 4?
The one that's due this Thursday is already open. You can get it. So yes, I don't have
Okay.
labs open till I finish the material. So the
Gotcha.
lab that opens on the lab that opened last Thursday and is due this Thursday, the lab due the 11th, is from chapter 4. And then the lab on chapter 5 will open this Thursday.
Alrighty, gotcha.
I want to basically give you a week to do the lab, and you shouldn't really do the lab till you cover the material. In fact, I would recommend, already having gotten a decent way into the lab that's due Thursday. But I don't procrastinate well. Okay, chapter 5, and we're going to start this chapter about energy by talking about not energy. I'm going to talk about work. Work, which uses the symbol capital W, has a really complicated definition right there, but it is defined as the component of the force that is in the direction of the displacement. That is if you push on a thing and you push on a thing with a force, it's how hard did you push and how far did you push it. If I take this block on a string and pull it to the side, the work would be how far did this thing slide from, there to there? What is that displacement? Not the distance it traveled, the displacement. And what force did I pull with? It doesn't give a shit how long took place. The fact that this is like 2 seconds or whatever, 2 seconds, doesn't matter. The velocity, the acceleration, doesn't matter. It's how hard did you push or pull over what distance. Though there is one other step to that, but I'll come back to. And in fact, if your force and displacement are parallel, work is just force times displacement, assuming they are parallel. See, in that complicated definition, I said the component of the force along the displacement. And so if I'm going to pull this block like I've been doing, the work is just going to be how hard did I pull at what and how far. However, if I pull it at an angle like this, and when pulling it this way, I can say my displacement was straight that way, but the force I applied was this way. If they are not parallel, you need to use the component of the force that is along the displacement. Which, I mean, you can break down components and solve for it, but that's kind of a pain in the ass. It's easier just to use this equation. See, the last equation was the assumption that force and displacement are parallel. If they are not, or even if they are, this equation still works. The real equation for work is that work is force times displacement times the cosine of the angle between them. Note, in this case, theta is not necessarily the angle from the horizontal. It is the angle between force and displacement. And so if I'm, that doesn't show up against my shirt. If I'm pulling it this way and the force is that way, this would be the angle. If I'm doing it like this would be the angle. If I'm doing it like this would be the angle. It is the angle between force and displacement. It doesn't matter if it's on the x-axis, y-axis, z-axis, or anything else. That work is just force times displacement times the cosine of the angle between them. Of note, the units of work is joules, is a capital J, where 1 joule equals 1 Newton meter. And I think that's all I have to say, though. Questions?
So to find our F, is that going to be given, or are we going to need to do any of that fun stuff from last chapter?
It could involve some of the fun stuff from last chapter. The net work would be based off the net force, because theoretically, like if I take something and pull with either side, well, right now I'm doing no work because there's no movement. But if I'm pulling with one hand and slightly pulling back with the other, it's just going to be the net force times the cosine of angle. So for the most part, it would just be like one thing pulling. Or if there's friction, you just say the force is, the pulling minus the friction. But we're not going to get too complicated with that.
Okay, great.
I'll keep it simple. There's one homework problems like that, but I say like, what is the work from this force? What is the work from this force? So you just do it individually for each force. So here's an example. This is stolen from the textbook, and it's so stupid I like to use it because what the hell? And it says, a man is pulling a sled of fish on some ice. The total mass of fish on sled is 50 kilograms. If the force is 120 newtons, and he pulls it for 5 meters. I should really fix some punctuation in here. How much work is done if he's pulling at 0 degrees? Which would mean basically how much work is done in this case. And then part B is how much work is done is he pulling at an angle like this. If you want to find work, it's force times displacement cosine of the angle. If he's pulling at 0 degrees, that means the angle is 0 degrees, where the cosine of 0 is just 1. And so if he's pulling at 0 degrees, the work will be 600 joules. If instead, if he's pulling it down and pulling at an angle, as shown in the picture above, be 120 newtons times 5 cosine 30. That's the general idea. Okay. Now, work is kind of interesting. Work is a scalar. It doesn't give a shit about direction. You don't say work to the right, work to the left, it's just work. And I've said before that scalars are always positive, though that is not true for work. Work is a scalar that can be negative and can also do some weird things. Let's say, for example, oops, wrong spot. I take this guy from chapter 4 and I hold him here and I move him to the side. If you look at the force, I'm applying a force straight up when I hold this. That's the tension up, right? So I'm applying a force up. But if I move like this, I actually do no work. Anytime your force and displacement are perpendicular to each other, the work is 0. That if you pick something heavy up and just move it across, it means no work because your force is up and your displacement is perpendicular. So it's of note, it's tiring. It's going to feel like I'm doing work if I keep my arm out here all day. But physics-wise, this is no work at all. Work, as I said, can also be negative. Let's say you're lifting a weight up. If you're lifting a weight up, you are, show this. When I lift this up, I'm applying a force upwards and it's moving upwards. So the angle between them is 0. So it will require work. But if I take this instead and put it down, if I'm putting this down, what's going to happen is I'm not applying a force down when I put this down. If I apply a force down, I mean like throwing it. I'm holding it up and just decreasing. But I'm holding it up while it moves downwards. There goes that arrow. That means there's 180 degrees. When I take this and do that, there's 180 degrees between my force and displacement, where the cosine of 180 is -1. And so that if I take this and just move it downwards, I'm doing negative work. And that's doable. In reality, positive work means you're making something do something it wouldn't do naturally. Negative work is you're making something do what it would naturally slower. If I take this ball and drop it, it would just fall. If I take this ball and put it down, I'm slowing the rate of its descent. That's why it's negative work. I'm keeping it from doing what it naturally wants to do. But yes, work can be negative.
I don't get why theta is 180 instead of like 90 or 270 if we're going up and down.
Well, because you're measuring the angle between the two. You don't measure from the x. You measure the angle between force and displacement. And so looking at this picture, the bottom one here, so if force is straight up and displacement straight down, there's a 180 angle between that. It's always the angle between force and displacement. Does that make sense?
I guess I want it to be 0 and not 180.
But they're pointing in opposite directions. The top picture is 0 degrees. Because force is up, displacement is up. That's 0 degrees. But in the
Okay.
bottom picture, one is up, one's down. They all They're 180 degrees apart from each other because they're pointing in opposite directions.
Okay.
This would be 0 degrees. That is 180 degrees.
All right. Okay.
For the record, for those of you who have some calculus, this equation actually is a shorthand. Really, the equation should be that work is the vector of force dot product to the vector of displacement. But I assume most of you don't know what a dot product is. So, and if you do, there you go. If you don't worry about it. Now, this chapter isn't called work though. The name of this chapter is energy. And see, I'm doing work here to introduce the idea of energy. And I'm going to introduce it with the work energy theorem. You see, I'm going to do some really backwards definitions here. But in general, energy is a complicated thing to really define. Like, I can talk about energy, and I talk about energy all the time, but what it actually is a little nebulous. But energy, what it is the ability for something to move, or the effect of it moving. It's a way to talk about how we're going to move things around. As I said, it's a weird thing to define. What work is defined, other than force times displacement cosine the angle between, is when you do work to something, you are changing its energy. And actually, to be more specific, you're changing its mechanical energy. You see, energy has a lot of forms. There is chemical energy. This is when you eat food and you give yourself energy to move from eating. That's chemical energy. Or you burn something, you set on fire, that's releasing chemical energy. There's nuclear energy from splitting a nucleus. There's electric magnetic energy. You plug something into the wall, the lights glow. There is, it doesn't say it here, but there's electroluminescent energy, the energy of light. There is thermal energy, the energy of temperature. And there's mechanical energy. And in this chapter, we're going to talk about mechanical energy. Mechanical energy is the energy of movement. It is how much energy something has from the process from it moving or from its location. And in all cases, no matter what you do to something, the total energy is conserved. Energy cannot be created or destroyed. It can just come from one way or another. This light right here is shining because it's taking electrical energy and turning into light. It's going from one form to another. Work, that being said, okay, let me rephrase this. You cannot create or destroy energy. It can only come from one place to another. But when I take this thing and pull it, I'm giving it a type of energy by moving it. That energy is not coming from nowhere. It's coming from me. The food I ate that morning is giving me energy to pull that thing. And although you cannot create or destroy energy, you can talk about the change in energy anyways. Because I can say that as I pull this thing, there was a change in energy of the block. That change in energy didn't come from nowhere. It came from me. I pulled it. I gave it energy. But on an individual thing, you can talk about how its energy changed because it was taken from somewhere else or going somewhere else. And when you change the energy in something, that is work. Work, by definition, is the change in mechanical energy. And so whenever you do work, you're changing its mechanical energy. Well, mechanical energy comes in two flavors, kinetic and potential. Really, all the types of energies kind of have a weird version of kinetic and potential. They sometimes have different names. Like in electrical, it's current and voltage, but current and voltage are kind of kinetic energy and potential energy. It's complicated. That's a physics 2 topic. But when you do work, you change the mechanical energy, which means you change the kinetic energy or you change the potential energy. Normally, the kinetic. Now, before I can really get into this, I have to say, there was two types of forces in the world, conservative forces and non-conservative forces. When you do work to something with conservative forces, any work you do will only change the mechanical energy. That if I only push on something with a conservative force, the mechanical energy will change. And the amount of change to the mechanical energy will be the amount of work I do. Non-conservative forces, some of the energy might change form. Friction is a non-conservative force. You see, if you rub your hands together, they get hot. And anytime you have friction, things heat up. When things heat up, that means they're gaining thermal energy. And so if you have friction, some of the work you do will go and change the kinetic energy. But some of the work you do will instead change the temperature. That is a non-conservative force because some of the energy changed forms. It went from mechanical to thermal. For the most part, we're only going to look at things that are conservative and ignore energy going to other forms, for now at least. Now, of note, if you have conservative forces, the work you do to something will be path independent. If I move this ball from point A to point B, and I only use conservative forces, the work to get from A to B will be the same in all three paths. That the force times displacement cosine angle will be the same for all three with conservative forces. They will be path independent. Gravity is a conservative force. Springs, which we're going to talk about next class, is a conservative force. Anything with magnets or electricity are conservative forces. Now, if I take these two magnets, push them together, and shoot that guy off, that's a conservative force. Non-conservative forces are path dependent. Friction is a conservative force. And if I move this book from point A to point D, and if I go straight there, A to D in the blue line, or the long way, A, B, C, D using that orange line, that it'll take a different amount of work which path I take because there's friction. And friction is a non-conservative force. Okay? As I said, we're going to look at conservative forces in this class. It gets complicated when you have non-conservative forces. But when you work on something with either one, conservative or non-conservative, you're changing the energy. But when you push on something with conservative forces, you are only changing the mechanical energy. And the mechanical energy is all going to come, the work you do will equal the change in that mechanical energy. Well, once again, the mechanical energy comes in two flavors. Potential energy, which we'll come back to. Oh, why did that just go back? And kinetic energy. Kinetic energy is the energy associated with the motion of an object. Well, kinetic energy, I use just KE. Some people use E_K. I just use KE. And mechanical kinetic energy, which is also thermokinetic energy, which we will cover in this class in the next to last chapter. Yeah, next to last chapter. But mechanical kinetic energy, which is in the unit of joules, is 1/2 mv squared. That the mechanical kinetic energy of an object is just 1/2 its mass times its speed squared. That's how much energy something has that is moving. At least how much mechanical energy something has as it's moving. And so if I take if I take this cart and have it go down this slope, when it goes down this slope, it's speeding up. It's speeding up means its kinetic energy is getting bigger and bigger and bigger. That it's gaining kinetic energy. That kinetic energy is going up because work is pulling it down. Work due to gravity. Gravity is applying a force down, it's moving downwards. That is going to cause a work. That work would change its kinetic energy. Okay? Now I keep saying it out loud, but I haven't actually really written it out. Work is change in energy. But really when you do mechanical, we're just going to say work is change in kinetic energy. You see that if you are doing work and you have only conservative forces, it will start speeding up. And so we'll just define the network being the sum of work from all the forces. That, if I pull on something one way, then pull on something another way, and the forces in each direction, the sum of the network from all of the forces will be your change in kinetic energy, where a positive work means the object is speeding up, and a negative work means it's slowing down.
Wait, so we're only going to be dealing with mechanical kinetic energy in this class, or?
In this chapter.
Oh, and this
We are
chapter.
going to introduce a different type of mechanic kinetic energy in chapter 8, and we're going to introduce thermal kinetic energy in chapter 11. And if you take physics 2, I'll get into electric potential, electric kinetic energy.
Gotcha.
All right, now this example is normally done with me dragging a bag across the room, but we're not going to do that because we're not in a room. So let's say I pull on a bag. In this case, that bag being a wooden block. The net work for me to pull a 2-kilogram bag across the table is 25 joules. If this starts at rest, what's its final velocity? See, here's the thing. We can say work is change in kinetic energy. That means work is final kinetic energy minus initial kinetic energy. If you know how much work is done to something, and if you have conservative forces, I'm going to assume conservative forces here, we'll just say work will be 1/2 mv final squared minus 1/2 mv initial squared. Now in this problem, it did say it started at rest. And so the work I do is just going to be the final kinetic energy. I can multiply both sides by 2, divide both sides by m, and square root. And plugging in some numbers, I can get a value. Now, as I said before, if you have friction, what's going to happen is if you have friction, work is still changed in kinetic energy. That's true. It's just there's thermal kinetic energy. Temperature is related directly to the kinetic energy of the individual molecules. This is going to be the idea called internal energy. Once again, we'll cover this in chapter 11. If you have friction, things heat up. Work is still change in kinetic energy. It's just some of the kinetic energy will be mechanical kinetic energy, 1/2 mv squared. Some of the kinetic energy will be internal kinetic energy. Well, internal kinetic energy is 3/2 a constant times the temperature of the object. This is going to be for a later chapter. Don't need to worry about it now. But know that always work will cause the change in kinetic energy. Now, let's look at that coat I had again. When I put this at the top and let go, it goes down the ramp, right? As it goes down the ramp, it's going to speed up. And this thing is made to be nearly frictionless because of the way the bearings are. So I can ignore friction here. As it goes down, it's going faster and faster and faster and faster. That's because it's gaining kinetic energy. And I can say it's getting energy by the work due to gravity. But I can also say, if I wanted to, that the reason it speeds up when it goes is because it started at the top of that hill. If it didn't start at the top of the hill, it wouldn't have been able to go down it. Likewise, if I use that other path, I can say that this thing speeds up when it goes down and slows down when it goes up. I could do this with work going down and gravity's down, and if it's going down, positive work, when it's going up, negative work, and work it out that way, pun not intended. But it's easier just to say, you know what? That kinetic energy came from somewhere. Instead of working all solely with work, let's just say that kinetic energy came from a different type of energy. And we're going to call that the potential energy. Potential energy is the energy stored in an object due to its position. It's energy that isn't doing anything yet, but waiting to go. These magnets, if I take the magnet and flip it, and then hold them together and hold it there, you know what? Okay. So if I take this magnet, flip it, and hold it here, it is right now doing anything because I'm holding it, but it's waiting to go. The second I let go, it's going to go shooting off. That's because I gave it the potential to do something else. I got it ready to go, that I then can't even see it fly so fast, that I got ready to spring off. Likewise, you take a spring, like this monkey's arms, weird sentence. If I take this and pull back, I'm getting it ready to fire. That the second I let go, it's going to fire upwards. I'm not actually making it go anywhere. I'm just getting it ready. And likewise with gravity, that if I take something and lift it up, I'm preparing for it to fall. That is potential energy. That by putting this code at the top of the ramp, I'm giving it the potential to be ready to go down the ramp. Now, potential energy can have a few forms, and we're going to do 2 of them this chapter, but only 1 today. On Wednesday, we'll talk about potential energy from a spring. That when I pull this guy's arms back, how much potential energy I'm building up to go shooting. But for now, we'll talk about potential energy due to gravity. Anytime you lift something up off the ground, you are getting it ready to fall. And as you get it ready to fall, the potential energy due to gravity will be mgy. It will be the mass of the object times g, where g is g, that is always g, 9.81 meters per second squared. And y is how high up the object is. It's how far up it gets lifted. Okay. Now, there is one kind of issue with this. Now, this is gravitational potential energy near the Earth's surface. There's another equation for it, like in general, if you're not on Earth or in space or whatever, but we're not going to bother with it. But this y. Y is how far the object is lifted. So, let's see if I can put something that you can see. Okay, this box of Kleenexes, you can kind of see it. Let's say I take this Tetris block and I lift it. I can say I lifted it like a few centimeters, that's it, right? But if I then go and push myself backwards, it's now over the ground. And I didn't change its height. Here, if I drop it, it'll just go boop and fall. But here, if I drop it, it'll go and fall pretty far. When you measure height, it's kind of the things of where do you measure from. That in this picture, I have those 3 books, A, B, and C. I think it's supposed to be a book. I'm not exactly sure. Are all at the same altitude. But if I want to measure their height, well, for book A, I'd probably say its height is this far. For book B, I'd probably say it's this far. For book C, I'd probably say it's this far. But I haven't changed the altitude. You got to think of where you're going to measure the height from. When doing potential energy, you can measure the height from wherever the hell you want, as long as you're consistent. That in a given problem, you pick your 0 point. And once you define your 0 point, you just always use that 0 point. That if you measure that your 0 point is, if you measure that your 0 point is this table, that's fine. Just note that if the book ever drops below the table, that if the book ends up down here, I have to say it's below the 0 point and has a negative height. I like to always make my 0 point as whatever the lowest point is to not deal with negatives. But it's fine. Make it whatever you want. And above the 0 point is positive, below the 0 point is negative. Now, those of you fully paying attention might realize I kind of have contradicted myself once today. A few times, actually, but it's weird. I said, first off, you can never create or destroy energy. And then I said work is change in energy. Once again, those are both true. You can't create or destroy energy, but you can move it from one object to another. That when I lift this, it's energy from me going to the thing. So I can say this had a change in energy. It just came from somewhere else. But more importantly, I said work is change in energy, but then I said work is change in kinetic energy. Here's the thing. Work, which is force times displacement cosine angle. Normally, you just treat it as work is change in kinetic energy. But you can do work to change the potential energy of an object. Let's say I take this book, and it's going to start a height y initial from the table, and it's dropped till it's at a height y final. I'll say the work will be the force times displacement cosine the angle. Now it's moving downward, and as it moves downward, It's being dropped, so it's due to gravity it falls downwards. So that means the angle is 0 degrees. So in this case, work is just force times displacement in y. And if this book is just being dropped, the force pulling it down is gravity. So the force is mg. And the change in y is just y final minus y initial. But take a look at this problem. If it's being dropped, y initial is bigger than y final. That means delta y is a negative number. But the force was down and the displacement is down. And so if the force is down, the displacement is down, using my F equals delta x cosine theta, work should be positive. But plug into the equation, I get a negative, which makes no sense. And here's one of the things. When doing work potential energy, what we say is, since potential energy is mgy, is that work is change in kinetic energy, final minus initial. But work is negative change in potential energy. That work is initial potential energy minus final potential energy. That when you do work to something, when you do positive work to something, you increase its kinetic energy. But when you do positive work to something, you also decrease its potential energy. And that anytime you do work, it'll be, assuming positive work, increase in kinetic, decrease in potential. And so work is change in kinetic energy, as I said before, but it is also negative change in potential energy. And so when you do work, you can change both things, kinetic and potential, or only one depending on what you're doing. But they should be equal. Now, if
Confused.
sorry, what was that?
I'm still a bit confused.
Where'd I lose you?
Like, it was like when you were basically going back and forth, talking like basically like between potential and kinetic and like the work relating to them. Like you were like going back and forth, and I was just sitting there like, did I just hear a lot of stuff at once, and now I'm confused?
Yep. Luckily, I'm mostly doing this to derive and not for solving problems, which is a good thing because this is really goddamn confusing. But let's see if I can try this better. If you do positive work to something, keep in mind you could do negative work to something too. And negative work is just everything I'm about to say would switch directions. If you do positive work to something, you can increase its speed. If you increase its speed, you increase its kinetic energy. But if you do positive, when gravity does positive work to something falling, as I show right here, that is going to be a negative value using the equations that we've already covered. And so what we say is, instead of work is change in potential energy, we say work is negative potential energy. That if you do work on something, you increase its kinetic energy and you decrease its potential energy. If you do negative work on something, you increase its potential energy and decrease its kinetic. That is the logic.
I get it. I get it now. All right, that's a little better.
Okay. Now, since change in kinetic energy is negative change in potential energy, what I can say is, let's say we have two cases, an initial and a final. So work then is final kinetic minus initial kinetic. And potential energy is flipped, initial potential minus final potential. Well, if I take this equation and add initial kinetic energy to both sides, and then subtract final potential energy from both sides, I get this. And what this equation says is kinetic plus potential final equals kinetic plus potential initial. And this is my goal here. This is what I'm trying to get to. If you have only conservative forces, aka no friction, if you have no friction, mechanical energy is conserved. Energy is always conserved. But if you have no friction, your initial mechanical energy equals your final mechanical energy. That your kinetic plus potential final equals your kinetic plus potential initial. And so going back to my quote on here, I can say that at this height, it has a certain amount of potential energy. It starts at rest, so it has only potential energy. And I can figure out exactly how much potential energy it has there. It's mgy. As this goes down the ramp, its total energy never changes. And that as it goes down the ramp, what's going to happen is its potential energy is going down. Its potential energy is going down because its height is going down. But as the potential energy goes down, the total energy doesn't change, which means it gains kinetic energy and goes faster and faster and faster down the ramp. If I switch to the other coat, right now it has only potential energy. As it goes down and then back up, at all points the total energy is the same. So let's say right now it has 100 joules of energy. Right here, it still has 100 joules of energy. Here, it still has 100 joules of energy. Here, oh, there it's dead. Here, it still has 100 joules of energy. At all points, it has the same amount of energy. It's just it switches from potential to kinetic. And as the potential energy goes down, the kinetic energy goes up. But the total energy is the same. Note it doesn't care about the shape. Both this ball A and ball B in this drawing have the exact same potential energy because they're the same height off the ground. It's just mgy. It doesn't matter. If they roll down the ramp, they'll have the exact same energy at the bottom of the ramp too, which means they'll have the same speed at the bottom of the ramp because energy will be conserved. Now, once again, this is assuming no friction. This is conservation of mechanical energy. Really, though, energy is always conserved. If you have friction, this is still true. It's just kinetic energy. Some will be mechanical kinetic energy, 1/2 mv squared, and some will be temperature. Some will be the thing heating up. But sticking to my little racetrack idea, that when this racetrack goes down on this thing, the whole time its total energy is the same. And every time it goes up in height, the potential energy goes up, so the kinetic energy decreases. When it goes down in height, the potential energy decreases, so the kinetic energy increases. But at all points, the energy is the same. Kinetic plus potential. Now, let's look at that in terms of my racetrack here. I've shown both cars going individually, but let's look at both cars going at once, like so. Right now, when I start, both cars start at the exact same height. They both started at 0.595 meters from the top of the table, where I measured, this is kind of off the edge of the table, but I measured it once before with a bigger table. So they both start at the exact same height. And as they go down, they both pass through this photo gate, which the pause symbol just covered. They both pass through this photo gate right here at the exact same height. And both of them started at rest. What I can say is it doesn't matter what happens in the middle. It doesn't matter that one takes the direct path and one goes down and back up. I can say that the total energy can be conserved. And even though they have different paths, they started with the exact same energy because they started with 0 kinetic and at the same height, so at the same potential energy, which means at all points their total energy must be the same. And when this red car hits that photo gate, and then this yellow car hits that photo gate, they're at the same height. And so they must be traveling at the exact same speed there. Because conservation of energy. Initial energy equals final energy. Or kinetic initial plus potential initial equals kinetic final plus potential final. Now, in this case, in this example, they both had no initial velocity. And so V initial is just going to go away. And if I look at this equation, every single term has an m in it. There's just m's everywhere. And since every term has an m in it, I'm going to divide out an m, which gives me this equation. I'm going to come back to this line in a second. But for now, say if I want to know how fast they're going when they hit the photo gate, I can subtract GH final from both sides, multiply both sides by 2, and I can plug in those numbers, which I did, and square root. And I can say that the speed these cars are going when they hit that photo gate, that the velocity at that point when they hit that second photo gate, I know what it has to be. It doesn't matter what path it took. That must be the velocity. Now there is a photo gate though, so I actually can measure exactly what the velocity is. And I'm going to be honest, it's not 1.53. It ends up being like 1.2 and 1.3 respectively. The reason why is because there is friction. Some of it is loss of friction. This assumes nothing is.
So, it makes sense when you do out these equations, but can you kind of just talk through it with the video one more time?
Okay. So right now they have the exact same amount of potential energy, and they have no kinetic energy because they're not moving. They have the same potential energy because they're at a set height. That right now they all that high off the table. Well, they're off the table, but whatever. So that's the potential energy. At every other point, their energy. Oops, that's not what I want. At every other point, their energy is going to be kinetic energy plus potential energy. But the total energy is never going to change. And so if it moves downwards, its potential energy decreases. If its potential energy decreases, its kinetic energy increases because total energy is the same. If it goes upwards, its potential energy increases. Therefore, the kinetic energy decreases because the total energy is the same. And that's true for both cars. But at the end, when they both pass through the photo gate, they both, oh, damn it. When it restarts, it resizes, and it's really annoying because I'm drawing on it. Ah, I have the drawing tool still on. Okay. Damn it. About there. When they hit the end, they both are at the exact same height. They're at this height right here. So they have the exact same potential energy. And since the total energy is the same, and they started with the same amount of total energy, they end with the same amount of total energy. And since if I know the PE for both, I can solve for the KE for both. Does that make sense?
It does. I'm failing to understand how they have the same speeds.
Because the energy is the same. They don't always have the same speeds. The red car is going to move a little faster at different parts. The yellow car is not going to, but the red car is going to speed up and go faster at the bottom, but slow back down on the way up.
Okay.
That at this point, conservation of energy says they must have the same velocity at that point. Not average velocity over the trip, but just velocity at that point.
Okay. Okay.
Other thing I want to stress, if you look at this conservation of energy problem, this last step before I plugged in numbers, I had V final squared equals 2 GH initial minus GH final. Really, if the initial wasn't 0, and I just trust me on this, I'm just going to add it in. If the initial wasn't 0, it would have actually been this. I can factor a G out of that. And if I swap the order of those, if I swap the order of those, means a negative sign comes out. I get one of the kinematics equations. This equation that we were covering in chapter 2 comes from conservation of energy also. That gravity follows conservation of energy. It's kind of an interesting side note. Now, this is assuming no friction. If there is friction, conservation of energy breaks down, or conservation of mechanical energy breaks down. If there is friction, what we can say is that all work done by non-conservative forces will be the change in total energy. That the total energy, total kinetic, or total final energy minus total initial energy, how much that changes, that would be how much energy is from non-conservative forces. That this truck dragging whatever it's dragging here is going to have, that means there's heat coming off, there's friction, there's going to be some energy lost. But once again, we're only going to work about with conservative forces and deal with what happens when energy is conserved. That does lead us to our first real example problem, which is going to be about ski jumping, but I only have a minute left, so I'm not solving this today. And so I am going to stop here, and I will pick up Wednesday, where I will do one example problem, and then I'll talk about springs, which I'm not going to lie, the spring bit is one of my favorite bits to teach for this class because, well, in person, I have some really good demos for it. Out of person, just videos of me doing them, but it still have some fun. But other than that, unless there's any other questions, I'm going to stop there.
Mr.
Oh, yep.
Schweidenbach or Dr. Schweidenbach, could you go back a slide for a second?
Yep. This one?
Yeah.
Any other questions? Right. I'm going to stop recording. So, bye.